So yeah, I would like to start thanking the organizers for the invitation to present the work here, and also apologize in advance. This was a short notice talk, so might be missing some reference in the talk itself. So the title of my talk is Sketching Amplitudes for HPT, which stands for Heavy Particle Effective Theory, and this is based on two works done in collaboration with Kees Haddad and Andreas Helbert last year. The first one is called On-Shell Heavy Particle Effective Theories, and the second one is where we describe tidal effects for spinning particles. And my talk will be divided on these two papers. So in part one, I review a bit the heavy quark effective theory and the heavy black hole effective theory developed by Paul Darmgard and Kees and Andreas, and then some review a bit on the massive spin-resistive variables developed by Arkani Hamed, Wang, and Huang, and then how we introduce the HPT variables based on these massive spin-resistive variables and the 3-point amplitude. Afterwards, we see how we see the Kerr black hole as 3-point amplitudes in these variables, some classical limits and spin universality. And in the second part of the talk, we construct an action for the tidal effects of spinning particles. We calculate the scattering amplitudes and also some classical observables from the scattering amplitudes, diagonal phase, and classical observables from the diagonal phase. So the motivation of this talk is that we want to use particle physics methods to calculate classical gravity, as we've been listening a lot in the previous week. And here we offer a different view, a new particle physics method to calculate classical gravity, which is the ideas and of heavy quark effective theory. Okay, so what is again heavy quark effective theory? Is a limit of QCD where you have a heavy quark interacting with light degrees of freedom, and these light degrees of freedom carry a momentum which is way smaller than the mass of the heavy quark. So at the age C, this is very useful when you're trying to describe, for instance, the B meson decay, which has a heavy quark inside, like the B quark, which has a mass of order 4 GeV, and then the interaction scale is lambda QCD, which is way smaller than the mass of the heavy quark. So it's a very useful limit to describe this kind of system. And in such a limit, you write your heavy quark momentum as the mass times the velocity, the velocity, plus the residual momentum. And this residual momentum will be order lambda QCD and way smaller than the mass of the heavy quark. And the nice thing is that in HQT, all the propagating degrees of freedoms are massless. So if we follow the KMOC, we can restore the H bar, the residual momenta, and now we describe the residual momenta as with a wave number and the H bar in front of it. So these ideas are useful for gravity because in the gravitational scattering, we are looking for a long range scattering of two heavy bodies, and you have a similar hierarchy as HQET in this problem because the exchange at graviton momentum is way smaller than the mass of the objects that you're trying to look at. So if you think about this type of diagram, the T channel, and you set your residual moment of the initial particle to be 0, that you can always do. The final moment of the particle 1 will have a residual momentum, which is the exchange at the graviton momentum. So again, we follow KMOC to restore the H bar in the residual momentum, since it's a massless propagating degrees of freedom. And the nice thing of HPT expansion is that in the Lagrangian sense is organize the terms in the operators in powers of Q over M of the heavy mass, and then if you restore the H bar, you organize in H bar, in powers of H bar. So it's a very nice organization of the operators that you should include in the Lagrangian set. Okay, so in 2019, the Paul Damgard, Case, and Andres introduced the heavy black hole effective theory, where it's the heavy quark effective theory, but coupled to gravity now, and using the Lagrangian description and the Feynman rules, they calculated the classical and the leading quantum contributions at 1 p.m. and 2 p.m. for scalars and for spin half fermions. However, if you want to go to higher spins, this becomes a non-trivial job since you're dealing with Lagrangian. So it's nice to input ideas from on-shell methods and describe the on-shell heavy particle effective theory that I'm going to describe soon to upgrade to higher spins, right? So before going to this on-shell heavy particle effective theory, I remind a bit the massive spinor-helicity variables developed by Ahkani, Hamed, Huang, and Huang. And in such description, you see that your massive momenta now requires two sets of the spinor-helicity variables that now carry the SU2 little group index of the massive particle, right? And this can be this lambda and lambda tilde now can be related to the square and the angle brackets. And with such variables, you can then write your Dirac spinors and your polarization tensors and polarization tensors for higher spins. So your Dirac spinor has the lambda and lambda tilde inside it, and there's a lot of information that you can recover when you take the massless or the high energy limit of these variables, because you should recover the massless spinor-helicity variables. In the bottom left, I lay down the minimal coupling of two massive particles with the same spin and a massless particle with helicity h. So this is particle 1, particle 2, and this is represented by Q in the amplitude. And this is the minimal coupling, and the minimal coupling is described by the most well-behaved amplitude when you take the massless limit. So this will involve angular bracket of the two massive particles, which one here, to the power of 2s, where this bold notation means that you have a symmetrization of the little group of the same particle. You also have an X factor in the amplitude, which is the constant of proportionality between your angular brackets from Q and P1 times the square bracket. Okay, so how we define the HPT variables? It's a very simple. It's from the Dirac spinors. So from before, we saw that we can write the lambda and lambda tilde as a function inside the Dirac spinors. And here there's a relation from heavy quark effective theory that the heavy Dirac spinors is related to the normal Dirac spinors via a projector. And if we input the lambda and lambda tilde here in the Dirac spinors, and we call it here the lambda and lambda tilde, but with heavy, which are the HPT spinor-helicity variables, you obtain a relation between these two variables. So the heavy, the HPT variables, they have a subscript v, which is just labeling the velocity of the particle. And if these two variables, the angular and the square bracket, they have a momentum associated. And the nice thing is that this momentum associated with these variables, they are proportional to the velocity of the particle, regardless the residual momentum that you have. The residual momentum will enter in the constant of proportionality in this way. So the very interesting and important thing on the for these variables is that if you calculate a spinless object for using the direct heavy spinors, they will only be related to the angular and the square brackets with massive particles inside. So this is a u bar u here, and then you only have massive the massive momentum inside. However, if you calculate a purely spin effect, you start to enter with the x factor and the massless momentum in the angular brackets or in the square brackets. And this is it's a spin operator in the on-shell sense. So this is a very clear splitting between spinless and spin effects, which will be very useful afterwards when we try to draw conclusions. So coming back to the Afghani-Hammond, Wang and Wang description of the massive spinor helicity variables. So they write general 3-point amplitudes. And here I'm just writing the general 3-point amplitude of two massive particles of spin S, so same spin and the massless particle with helicity H, and this comes as a sum where you're increasing the numbers of this type of operators. That is the spin factor. And, well, this is the positive helicity in the chiral basis, meaning that you only have angular brackets in this sense. So, but it's similar for also for the negative helicity case. However, this is not a clear separation between spinless and spin effects, because the traditional variables, which is this angular, they hide the spin and the spinless effect, as we're going to see in the next slide. So just to mention, the minimal coupling from this 3-point amplitude is the best behaviored amplitude, and is the first one. Here is that what I've shown before in the previous slide. Okay, so how does this amplitude will look like if you use HPT variables? So if you use the relations that we can obtain between the angular and the angular brackets in the traditional spinor helicity variables and in HPT variables, well, you obtain this relation and substitute in the previous formula, and you obtain the most general 3-point amplitude of in written in HPT variables. And the interesting fact here, as we can see from this relation already, is that as you increase in K, you're including more spin effects, but this is a clear separation here between purely spinless and purely spin effect, as are shown from the direct spinors sense. So this is what I mean by in the traditional variables, you mix between spinless and spin effects. So this is the most general 3-point amplitude from HPT, and we call it the coefficients that come in front of each term of the amplitude, the G heavy, and they are related to the traditional coefficients by this formula. And if you remember, the minimal coupling from the high energy limit in the traditional variables written like this. So if you look for the formula, so for S, so S half, what you obtain is just this term, which has one spinless effect and one spin effect. Okay, good. So given that, we want to interpret, as was interpreted in the literature, the K black hole as with amplitudes. So in this set of papers, it was interpreted the K black hole was obtained the 3-point amplitude for the K black hole from this action. So the action has a multipole expansion, where each multipole comes with the Wilson coefficient, and the Wilson coefficient has the Wilson coefficients have the information of the internal structure of the body. And when all these Wilson coefficients are 1, this represents a K black hole. So what we do is that given this, that the 3-point amplitude into the traditional variables were obtained from this action, we recast these amplitudes in the HPT variables, and we obtain this type of the amplitude. So this amplitude, however, so you can see here the Wilson coefficients. It's written, however, it's written in a mix of two bases. So you have the chiral basis with angular brackets, and you also have the anti-chiral basis with a square brackets. So what you want to do is convert back to one of the bases. So we convert to the chiral basis, and from this amplitude, what you obtain is the multiple expansion with the Wilson coefficients here. So if you compare this, the amplitude obtained from the action with the general 3-point amplitude of HPT, you can see that there is a one-to-one mapping between the G-heavy coefficients and the Wilson coefficients from the action, and the relation is given by that. So it's a one-to-one mapping between the coefficients with some factor. So now, if you plug here the minimal coupling, what you obtain, you plug here the minimal coupling, and then you want to understand what are the C of the Wilson coefficients of the action. What you obtain is that given that the minimal coupling is here, you obtain exactly 1 for the Wilson coefficients of the action. So this is very nice, because it means that the minimal coupling in HPT is precisely the multiple expansion of a K black hole, but also is precisely the same expansion of a gravitating body. This result was first obtained before in the literature up to order 1/s, and then was precisely obtained using some Hilbert space matching by these authors. But here the nice thing is that given the 3-point amplitude of HPT, we don't need to massage the amplitude in any way, or what it means that we don't need to do a Hilbert space matching or any boost on the amplitude to obtain the same multiple expansion as obtained before, as obtained from the action. So why is the reason that we obtain the same multiple expansion, and or was the reason that the traditional variables hides a bit this multiple expansion? Is that, well, these variables they hide the spinless and spin effect in such a way that if you want to translate from chiral to anti-chiral basis, you have always a spin effect mixing with what can be seen as a spinless effect, but is only seen as spinless effect when you look to the HPT variables. So for the HPT variables, we have a clear separation between what is spinless and what is spin effect. So you can see that there's a statement basis independent, right? So if you want to change from to chiral to anti-chiral, the spinless and the spin do not mix, and the same is true for the spinless. They do not mix, and the same is true for the spin effects, right? And another way to see this is that even though the particle 1 and particle 2, so this is 3-point amplitude, they differ by a null vector, the external states, so this HPT variables, they are related with the same momentum, because the momentum of the P2 will be proportional to the same velocity as the momentum as the P1 by a factor which has a null vector, which will be 0. So is the same momentum. And the mismatch on the traditional variables also can be seen that here for the spin vector, you have to choose either P1 or P1 or P2, and they have a no momenta differing for them. So for us, we can choose the V to be here in the spin vector. Okay, so given the 3 point amplitudes that we obtained, we can go on and calculate higher point amplitudes. So in the paper we calculated a boson exchange, so the channel diagram that we had before. But here I want to show the Compton scattering. So this is the amplitude of 2 heavy particles with general spin S and 2 gravitons with positive helicity. And if you use some BSFW, and this is the same helicity case, what you can see in the 4 point amplitudes is that you obtain a spinless term and a spin factor here. So this is again a clear separation between some spinless and some spin factor yeah, so this way of writing and in using the HPT variables also makes it easier to take the classical limit. What we also did is that we standard this result for n bosons, which has the same helicity, so only the same helicity case shows a clear separation between spinless and spin effects, where here you have amplitude with n plus 2 particles, where these 2 here are the same as the 2 massive ones here, and the n represent the n bosons that you can radiate. And when you calculate that, what you obtain is that is the same amplitude if you had some scalars radiating in bosons and the spin factor factors out for the same helicity case. So this is some spin universality. So here I come to the conclusions of the first part of the talk. That what I want to say is that the HPT variables, they allow us to extend the heavy quark effective theory and heavy black hole effective theory to general spin in an on-shell sense. And the H bar expansion it's clear in the on-shell amplitudes, and we isolate the spinless and the spin effects, allowing us to see a clear multiple expansion, which agrees in the minimal coupling agrees with the black hole, and also facilitate to take the classical limits of the 3-level amplitudes. And so this is what I have to say for the first part of the talk. Maybe we have some questions at this point. Okay. I guess I can move then. So for the second part, we describe tidal effects for spinning particles. And here I give a cake recital on what we do for that. Is that we use EFT tools, the Hilbert series, to enumerate all the possible number of operators that you can have of a particular type, so the grouping variants, and then you can construct a basis from that. So what we want to calculate is the scattering of 2 spin half fermions here, where we include tidal effects in this vertex here. So we calculate the triangle diagrams. So first we want to identify all the possible operators of such type, where all the possible contact interactions such that we can plug it here and calculate this 4-point amplitude. So to do that, after we enumerate over everything and construct the basis, we use on-shell amplitudes of this part of this amplitude to guide us on which terms are relevant. So if you have some off-shell relations, we can see them on shell. And then after that, we compute the tidal effects as 2 p.m. up to spin half. So these diagrams, which with all the possible contact terms that you can have here. So this is what the Hilbert series gives. And then with this scattering amplitude, we can calculate several possible observables. So this was based on some previous spinless case done by Case and Andreas. So I won't go much on the Hilbert series. I just want to say that the Hilbert series take as input the field content that you have in the contact term and the field representation of the fields, and then it spits you out the number of group invariants that you have given a number of derivatives. So we want to build the Hilbert series of two fermions and two gravitons. So this contact term here. So if you look closely to this two Hilbert series, so this is Hilbert series for odd mass dimension and an even mass dimension. And if you want to look for the number of operators that has, so this is the Weyl tensor that has two left-handed gravitons and one right-handed and one left-handed and one right-handed fermions, and the 2n minus 1 derivatives, what the number in front of this Hilbert series is the number of operators that you have of such type. So this is the floor of n half. However, the Hilbert series do not give you information on how you contract these Laurent indexes. So you need to construct a basis for that. And this is the hard work to construct a basis. So what you do is you start placing derivatives in the fermion fields and in the Weyl tensors, and then contracting the derivatives. Later on, you check on shell if two operators that you have constructed, they are related or not when you go on shell. So this is the odd dimension action, the odd dimension Lagrangian. And these are Wilson coefficients that comes along with the operators of a type. So if you note, this is it goes from n0 to infinity. So it's all the possible operators that you can have here. And I forgot to mention that the odd mass dimension case is analogous of the previously done by Case and Andreas on the complex scalar, where here instead of two fermions you have two complex scalar. The same was done for even mass dimension. So given that, you construct your basis, your in the Lagrangian, but now you have to check because sometimes you have some off-shell relations that are not so clear. So what we did is to build the amplitude basis for the gravity. Yeah, I forgot to mention that it's also done by for QED. So, but here we build the amplitude basis for gravity, where the helicity here are the helicities of the gravitons and of the fermions. And this is the possible terms that you can have in an amplitude basis. And of course, as you're placing a lot of derivatives, you start to enter the Mandelstam invariants. So this was used to guide us on how to construct the action, because the offshore relations are sometimes not obvious. Okay, so given these two Lagrangians, we can go on and calculate this diagram. So we calculate the 2 p.m. tidal effects, the leading 2 p.m. tidal effects for spin half particles. And what I want to mention is that the amplitude has some spinor structures, and so you have this calligraphic U and calligraphic E, and this is the monopole term, this is the spin orbit terms, and then you have the spin terms, which which comes with some contractions on the transfer momenta. So we introduce some form factors for each of the spinor structures here. So the monopole, the spin orbits terms, and the spin-spin interactions. And as you increasing mass dimension, you're going to increase here in this J. So I just want to show one example of this one, that what you have is that you have all your Wilson, this form factor has all your Wilson coefficients with some mass terms and with omega, which is the product of the two velocities, two incoming velocities. Okay, so given these amplitudes, so now since we have the amplitude here, we can go on. Okay, change the slide. So we can go on and evaluate the classical observables. So we evaluate several classical observables. We obtain the two-body Hamiltonian following the papers by Bern, Luna, Freudban, Shan, and Zhang. We also obtained the linear and the angular impulse follow KMOC. And from the amplitude, we calculated also the iconal phase. And another way to calculate the classical observables is from the iconal phase, and then we obtain the linear impulse, the spin kick, and the aligned scattering angle following the same paper. So I'm not going to focus much on the conservative two-body Hamiltonian. I will go to these two cases here. So first, from the KMOC, what you obtain is that the linear impulse, it's this big formula here where you have your terms of the monopole, of spin orbits, and the spin-spin term. I don't know how elucidating is that, but we obtain a big expression for all the tidal effects that you can have at 2 p.m. up to spin half. We also obtain the angular impulse, and I want to mention that the angular impulse, the needed part to calculate the leading tidal effects, has two terms. So it has this term here, which is the product of Q over the spin and the commutator piece. This first term, what will enter is the form factors of the monopole and of these 1-2 particles. So yeah, what I forgot to mention is that here is on the tidal effects on the particle 1 and not on particle 2. So if you want to obtain a symmetric tidal effects, you just have to substitute and symmetrize. But the commutator piece now here has the 1-1, so the spin orbit 1-1, and the spin-spin form factors. Okay, so keep in mind this commutator piece, and now we go along for the iconal phase. So for the iconal phase calculations, what we do is that we plug the obtained amplitude in this formula, so in the Fourier transform of the iconal. And following this paper, you can write your amplitude in the center of mass kinematics, where you have your spins defined there. Oops, sorry. Okay, yeah. So and you can write this amplitude in a basis of classical spin structures. So this is the monopole operator. You have some term that has a dependence on Q and S, and then 2 Qs and 2 S terms, which are the spin-spin terms. And what you can do for these operators is that you can pull it out from the Fourier transform. So our Fourier transform of the tidal effects will involve integrals of such type. So where here you are increasing in the mass dimension of the operator. So this integral here with the operators here, and then you can pull it out the operators and write it as a derivative of the impact parameter in an integral with only that. So it is I j plus 2 with some normalization. So in the impact parameter space, so you can write the operators in the impact parameter. So we call them the impact parameters operators. So they are similar to the upper ones, but now the Q is it becomes a derivative with respect to the impact parameter. So going along, what the nice thing of pulling out the operators that you can write your iconal phase. So the leading, this is the tidal part of the iconal phase as an operator acting on the integral with only depends on the impact parameter. And this operator, so this is the summation on the mass dimension, so it's increasing in J, and the operator can be written as a summation on the operator types here with some coefficients in the front. And just this is just a nice way to write. So you can see that when you calculate following this paper, when you calculate the linear impulse and the spin kick, when the linear impulse you have a derivative with respect to the impact parameter, this will only act on the integral. So you can write compactly as this, while the spin kick will only have a derivative in the spin, right? So it only acts in the iconal operator and not in the integral. And what we saw is that the linear impulses match perfectly with the one obtained from QMOC, while we obtained a matching here for the spin kick with the commutative piece of the angular impulse. We go further on and also calculate the scattering angle in the line spin case, where again the scattering angle has a similar derivatives, so that is the derivative of the modulus of the impact parameter, and it acts only on this integral. And what the effect of this is to increase one power here of the integral and pulling out some terms. So this is the compact way to write the scattering angle, the impulse, linear impulse, and the spin kick. And in the paper we show the explicit formulas, but here I just wanted to say a bit on this. To say a bit on these derivatives and how they act. So yeah, so this was a very short talk, but I come to my conclusions now that in part one, I already said a bit that we introduced these HPT variables, that they are very natural and they allow us to see the multiple expansion of a Kepler pole precisely, and also the multiple expansion of a spinning body, and they help us a lot to calculate the classical limit of 3-level amplitudes. And finally, I just shown that we use the EFT techniques, more precisely the Hilbert theory, to enumerate all the possible tidal effects that you can have it for spin half particles up to 2 p.m. And this was a function on the recent description for the spinless effect. And then we also use the Samon shell to guide us on this action construction, and we calculated several classical observables from that. I guess with that, I would like to thank you for the attention and for listening.
Thank you, Rafael. So we open the floor for questions. Yeah, Donald?
Yeah, thanks, Ricardo. Yeah, thanks, Rafael, for a nice talk. Yeah, maybe I missed it a little bit. I was interested in your comments about the relation between the spin kick and this, commutator bit of this angular impulse thing.
Mm-hmm.
I mean, I guess the angular impulse thing is supposed to be some observable, but it does have these two terms. So, do you know what's going on with that second bit? Or?
You mean why we see the difference between the two?
Yeah.
Yeah. So actually, we are not quite sure on that, on why we see the difference. But I can tell you what we did. So for the angular impulse, we calculated these two bits.
Yep.
And this bit has the commutator piece has the spin and the spin orbit, while this first bit only has the monopole and the spin orbit. And then we translated the angular impulse calculated in such a way to the center of mass kinematic in the similar to the other paper, and from the calculation of the spin kick, you only obtain this commutated piece. And maybe the interesting piece is that I think you can see from the impact parameter observables that when you calculate from the iconal phase the spin kick, you take a derivative with respect to this S, so you only obtain such kind of terms and one of them. So you don't obtain the monopole in that description. So it's a puzzling that yeah. So this is what we did, and we saw, but indeed you obtain the same part as the commutated piece. Exactly.
Yeah, that's interesting. I mean, I can't quite remember, honestly, the calculation I did with Justin and Ben, how it worked. But I seem to remember that we needed the two terms for everything to work out in the end somehow. So it's a bit funny to split them up. I guess the other bit is put somewhere else, but yeah, it'd be interesting to understand how that all fits together in the end.
You mean you need the two terms in the calculation of the angular impulse?
Yeah. You might remember rather than I do.
Yeah. I mean, yeah, maybe some definitions of how you have the spin definitions, but yeah, this is what we saw.
Yeah. Okay. Thanks.
Thanks for the question.
I don't see any other hand up. So maybe I can ask a question. So you might be aware of this paper by Lettier-Casal, almost 1 year old, about the formation of spinning black holes. So we know that Schwarzschild black holes do not deform in the static limit. So, but there is some debate about what happens in the static limit to spinning black holes.
Yeah.
Do you have anything to say to the deformability of the static limit of deformability of spinning black holes?
Not much, because this will be, well, this deformation will be entailed by the Wilson coefficient here, and I guess we need some principle on how to constrain such Wilson coefficients. So you can say that if for a K black hole they are zero or not. But,
yeah, but you need some sort of matching. You cannot say.
From this methods, I don't think so. Only if you use some scattering amplitude consistence of it to tell you about what are the Wilson coefficients. But yeah, you need to match somehow.
Okay, thanks. I don't see any. So if you can raise your hand, yeah, go ahead, Gabriel.
I have a question. Yeah, I cannot raise my hand. I'm trying to relate what you described to what I have been doing for many years about string scattering and tidal effects, for string collisions, because there, for instance, we find that the iconal phase is not purely real, simply because, through this tidal effects, the string gets excited. So the S matrix is only unitary in a Hilbert space, which includes other channels. So I wonder, your iconal is purely real, right?
Yeah. So when does, can you remind me when it becomes imaginary, the iconal in the
Immediately at lowest order,
okay.
in the size of the string divided by the impact parameter. So, as soon as you have tidal excitation, by definition, your string can become excited or changes its quantum numbers. So, in fact, I mean, I wonder, are you really describing tidal deformation? So it's just an effective theory of how, how a particle interacts with gravity at higher orders in curvature?
Yeah, you mean if we take, well, in the classical limit, what of the Wilson coefficients will survive or not should be describing the
I mean, it's only an effective description.
Yeah, indeed. Yeah.
I mean, you don't have a microscopic understanding of the tidal deformation, do you?
No. It's an effective description. Yeah. So these Wilson coefficients, it's they go high in the mass dimensions. So it's an effective description of this type of operator.
Yeah, what I want to say is that in the case where you have a specific representation of your spinning state, a string,
okay,
then you can look inside that blob, see what each string goes into, and we have a few papers with Paolo Di Vecchia, Rodolfo Russo, Da Polonio, where we say microscopic description of tidal excitations and so on. And somehow I don't think we have tried to rephrase everything in this language of yours. Probably we can make definite prediction on these coefficients.
Yeah.
In the context of a definite model, which is strings. But
yes.
so it'd be interesting to.
Yeah, it would be interesting to match I mean, because here we are agnostic on the blob.
Yeah, exactly.
Yeah, so it will be interesting to match the Wilson coefficients.
Yeah, I think there will be interesting lessons to be learned from the string example.
Yes, for sure. Yeah.
Yeah, maybe I could add to that. And there's Walter Goldberger and Ira Rothstein have papers, sort of recent work where they've been attaching to world lines like a Hilbert space, and and thinking about this as a way of modeling black holes. So the Hilbert space is just some space, of Gaussian modes on the event horizon, and they can do some pretty cool stuff with that, like look at scattering particles or Hawking radiation. I guess Ira talked about this, but I suppose you could use those methods to obtain the quantum contribution to the to these tidal deformabilities for, like, say, a Schwarzschild black hole. Maybe they've already done it.
Yeah, I mean, what I have in mind is that somehow okay, in the case of strings, the size of the object plays an important role, of course. So, for instance, you also didn't discuss things like love number or things like this, which.
Well, some of these
coefficients.
Yeah, some of these coefficients should be the love numbers. Yes.
Okay, so these are directly the love numbers. Okay.
Yeah. But but since we are agnostic, we don't have.
You cannot compute them. Yeah.
Not. Yeah.
Okay.
But we can. We for sure. Sorry.
Yeah. Go ahead.
No. Yeah. But for sure we can. We could compare with the world line approach. In the spinless case, it was compared with the one in the previous paper done by Kate and Andres. They compare with the world line approach.
maybe I could mention a slightly related thing. Well, one thing I noticed with Alfredo Guevara and Justin Vines and this Kerr black hole, you can somehow take this minimal coupling amplitude very seriously, and if you do that, you'll find that the effective action becomes quite string-like. You know, that's the two-dimensional effective action, an effective world sheet sort of appears. Kind of an amazing thing. But you know, it's quite a rigid thing, but somehow you know, there should be some relationship, I guess, with Gabriele's point of view on where these love numbers and so forth from that perspective.
Yeah, well, I mean, somehow what I'm missing is there an information that this is a black hole, or that it's a, you know, simply an elementary particle? For instance, when you have strings, you can, since you know the size of your object, you know whether it's inside its Schwarzschild radius or not. So can be, well, actually, when it is inside its Schwarzschild radius, it's a mess. We know there are big corrections. If it's big compared to the Schwarzschild radius, then it's a, you know, it's simply an extended object, but it's not a black hole. So it would be very interesting to see what this love number does as you go towards the black hole limit from being away from it. You see, when the string is large, then there should be quite a lot of deformability, but then when it shrinks, it should reduce itself. And I don't understand, okay, in this calculation, how you put in the size of the object relative to its Schwarzschild radius. So maybe you take the particle as being point-like, or...
Yeah.
Mm-hmm.
But yeah, we are in the, yeah.
It's not an intrinsically extended object, in other words.
Well, no, it's an effective description that I don't.
No, it's probably more a model of a black hole than a model of a long string. Okay.
I mean, I guess you could, you know, still, I mean, if the string is long but small compared to some impact parameter.
Oh yeah, it is small compared to the impact. That's what we do exactly. So
then you should be able to expand the string's effective action in terms of a world line with higher dimension operators.
Yes.
So the string would uniquely determine the coefficients of all these higher dimension operators.
Yeah, exactly. So this is the limit we are considering. So the Schwarzschild radius is small, and the string is bigger, but then the parameter is much bigger.
These would be,
yeah,
and these would be different to the ones that Walter and Ira are getting, because theirs are literally coming from the quantum dynamics, but yours would be coming from the G string.
Yeah. So,
I mean, I am drifting.
I am puzzled by
a... session. Go ahead. Please, Paolo.
I'm puzzled by one thing. I don't understand. Just naive. I mean, how can you have tidal effect if you have a point particle? I mean, usually there is in string. I understand. Here, you seem to have tidal effect even if there is no extended object. In what sense?
In the sense that when you see from long distance, this blob here entails all that could be here, that from the extended object, I think.
That means the blob is not is an effective blob. You don't know what is inside. That's the problem.
No. It's completely agnostic on what's inside. We don't know what's inside.
There is a very simple analog which I learned from like reading Ira's stuff. So it's the polarizability of a molecule. So you take a molecule and you put it in an electric field, it gets polarized, so it generates, you know, it responds. You know, the charges separate, but you can just you know, that's the microscopic model, charge separation. but you can describe that by an effective operator. Will be an E squared operator, because you have one external electric field that's be switched on to get anything, and then this thing generates its own electric field because the charges separate. It generates a dipole field. So there's an E squared operator for molecules, which describes polarizability. So this thing is just the same. It's a gravitational analog. You put the thing in the external gravitational field, and it changes shape, it generates its own gravitational field. It's a H squared operator, but it's tidal. But from the point of view of the operators, it's just an effective operator, particular structure. I don't know if that helps.
Yeah. Thanks for the comment.
Thank you. Yeah, it's more clear now.
Yeah, actually, the non-vanishing of that operator would be the fingerprint that it's a composite object.
Exactly. Yeah, that's the point. And you look at large distances, you don't resolve the structure, but you see the effective operator.
Yeah, exactly. Yeah.
But somehow there must, as Paolo is saying, there must be intrinsically some size of the object. Otherwise, it's very hard to see how you can have tidal effects. But
the mass, you mean?
Yeah, well, I guess it is. It's like this really is the prototype of a finite size operator.
Yeah.
Also, people say in GR that you cannot have, for the case of spin, you cannot have spin classically without having a finite size. So.
Yeah, I guess that's true. Somehow that always seems a bit different to me, but yeah, whatever. I mean, these love numbers are tidal deformabilities, etc. Really seem like you've got to have a finite size blob at some stage, but spin. Yeah.
Well, no matter spin in gravity, you cannot have also mass without a size.
Right.
That's why
exactly.
It's kind of puzzle that
tell that to the electron.
The formability of the black hole is 0 in the static case. It's still not. I mean, it needs to me not well understood in terms of an unsymmetry for this coefficient to be 0.
It's especially weird because it's in particular dimensions, right? So it's weird.
Yeah, it's only 0 in 3+1. So I was about to say that we are naturally drifting to the discussion session, which is good. But what is? Shall we pause 2 minutes to let people have a coffee, or are we afraid that nobody will come back if we pause 2 minutes?
Should I stop sharing?
I don't think we're supposed to be jail keepers. I'm trying to keep physicists away from their coffees. It's really unfair.
Actually, I don't know. I think there was a little bit of misunderstanding. They were supposed to be. I'm not sure we are planning a real discussion session today after the talks, but of course, if there are questions and if there is discussion, the better. But I don't know. It went into the program. I'm not sure we were really discussing thoroughly whether to have a separate discussion session at the end.
Yeah, I don't think there's a particular topic, but since the question sessions after the talks were quite short, I think it's an opportunity to discuss more about whatever we want.
Okay, just comment on this length of the object. I mean, roughly speaking, the length scale, if it is extended, it should just be the scale at which the high derivative operators on the world line action are suppressed, right? So there must be a built-in length scale.
Yeah, exactly.
Yeah, maybe it can be useful to think about the higher dimension operators suppressed by masses and radii if you don't want to introduce any H-bars. If you want to think of a classical effective action, so we don't get to trade radii and mass or distance and mass. So then there's a dual expansion.
Yeah, but specifically in an actual extended object, in the length shows up just in the world line effective action, the high derivative operators. That's where it would. hidden.
But that means that if you consider a string, all these objects are related to each other, probably. All the, in general,
yes.
for each term, you have a different quantity, dimensional quantity. But in case of string, you have only alpha prime.
That's
So,
right. It's just, on the string, it's just alpha prime expansion on the world line.
Yeah, I mean, it's alpha prime, but, well, how can I say? If you have a light string, a massless string, or a very light string, then it is really alpha prime in the sense that the string length enters. But you can take excited strings, which are very long and almost classical, and then they have their own length, their own size, which can be, you know, classical. I mean, at least this is how I see things, okay? A very light string is quantum, it's not. And it has a quantum size. But then excited strings, you know, are classical, like cosmic strings. And they can have any size, unrelated to alpha prime. Or if you want, their length is alpha prime times the mass order. So you can play with the size of your string and consider scattering of different states. And you can vary this parameter. I mean, it's not just a fixed number, the size of the string, of course. And in fact, if you go to very large spins, then the size becomes also typically large in alpha prime units.
Probably that's true for if you imagine another extended object, that the contribution to these operators may be just related to the extent of the object, but it may also be an interesting statement about how it interacts with other things that you have integrated out. And so it leads it to an effective scale or an effective effect on the operators.
I have another question. You wrote the Compton scattering amplitude. And there are no spurious poles there. Usually,
okay.
I mean, did you solve the problem or not?
No.
I see.
Yeah, so there's I've shown the same helicity case, right? And I didn't show the opposite helicity case. So in the opposite helicity case, well, you have this factorization between the spinless part and the spin part. And in the same helicity case, in the opposite helicity case, the leading in H bar contribution that for the Compton amplitude that factorize in such a way. So you recover this factorization in the leading H bar for the leading H bar part, but the spurious poles are still there.
So what is the problem? Can you explain, Paolo? Or?
I mean, from what I understand, there has been a lot of work using the 3-point function of the paper that you also mentioned, Arcani Ahmed et al.
Yeah.
And from that coupling, you seem to recover the behavior of the Kerr black hole. You get the exponential that you had also in the, and at the level of 1 p.m. But then in order to compute the amplitude at 2 p.m., you need to have one loop. And so you need the Compton. You need the
These Compton amplitudes that we showed.
amplitude. And on that formalism, there used to be a problem with spurious pole. So on that direction, I think the calculation stopped. I mean, there is no real at 2 p.m. including spin. Am I right or am I wrong? I mean,
yeah, you get the spurious pole for when you have high spin, like three halves, higher than 3 halves for the Compton with photons, and 5 halves for the graviton case. So you have spurious poles in the amplitude.
But did your general discussion depend on taking that form of the
yes.
3-point function?
I mean, it
Well,
seems to me that most of the paper start from that 3-point function.
But I don't know if Rafael's...
Well, for the, I think if you want to use that Compton amplitude to calculate that at 2 p.m. order for higher spins, you would have this spurious pole there. But
your general framework did not imply using that, or did
no,
it?
not at all.
The general framework. Mm-hmm.
For the HPT variables, no, they don't depend.
Mm.
And yeah, but we stopped it at the Compton amplitudes. Well, at the n boson radiated amplitudes. We didn't do loop in the first paper that shown.
I mean, that seems to be an abstraction in the case of spin in general.
I guess so, yeah.
Is that related just to the problem of coupling spins to gravity? Usually then you're forced to introduce new states.
Sorry?
Usually you're then enforced to introduce new states. You can't couple single spins to gravity.
Yeah, I think it's
Yeah.
exactly that.
Yeah.
You know, you don't expect to have a scattering amplitude that's well defined, you know, for these high spin particles. You know, it works at 3 points, but when you try and make 4 points, you know, then it's the interactions that crap out. So
Right.
it's probably exactly what you expect.
But that's because you just have one spin. No? That's because you just have one state. If you included a tower of them.
Yeah, well, you could maybe also include some higher dimension, you know, some contact term or something to get rid of these spurious things. Well, it's maybe not completely clear what you're supposed to do, but I mean, certainly, if you take the mass small, you know, something is supposed to break down. But you know, I mean, if our application is to black holes and you know, to classical objects, then presumably one can do something.
But the real question is ultimately what you want that higher spin theory to do, right? So
well, I want it to be a Kerr black hole, right?
You want it to be a Kerr black hole, but who says that a Kerr black hole is a single higher spin field?
Yeah, exactly.
Right? Ultimately, what you want that field theory to do is to give you a method to actually not use relations between Lorentz generators of large representations. That's what you actually want it to do. If we were smart enough to use spin a half, but not use that sigma I, sigma j is delta ij, then we would be in business already with spin a half. So with that in mind, you can cheat your way around and just not use a fixed higher spin, but use, as was said, a tower of spins from 0 to s, as long as you treat all of them uniformly. And then everything is cool, at least in principle.
And in principle, sounds like it's hiding some stuff.
It depends. I mean, it depends what you mean by hiding. I mean, yes, it's not a fixed higher spin, but
I suppose I want to do the calculations with loops.
Well, I mean, we did go up to spin 1, spin 2. Andres and Dimitrios went to S square, and they compared with Rafael's approach, which is different from this, and they seem to agree. So I don't know. It's, if there is something that's hiding, it's hiding at higher powers of spin than S square.
Mm-hmm.
Well, maybe let me interject here. Hi, everyone. Yeah, I mean, in principle, with Alfredo and Justin, we went to spin 4 and infinity just by plugging in very naive spurious pole ridden amplitude. just indeed at spin half we didn't expect any problems, and we are quite confident up to spin 4 in the aligned spin case result that we had. And I hope that it was all matched successfully by you guys. And right, I'm not sure it was exactly clear in the latest paper by Andres.
Yeah, I think they did I think they did match what you guys did. Yeah.
With the line spin.
Mm-hmm.
So yeah, we really don't know what happens after spin to the 5th power, and that is the highest spin problem that we just really don't know what to match to, because after all, we're plugging in a 4-point amplitude, which should reproduce a black hole only to the point that we know what the black hole is, and a black hole is a classical object, and all of this 3-point matching is well footed in the in that action that Rafael showed, the classical one that everybody agrees on, just the word line action for the curved black hole. But I don't think there is such an action for the to the high order in curvature. That's just I haven't seen any actions of this sort stated as being curved black hole effective actions. So I think the problem is not just the 4-point amplitude quantum; it's also the classical. What is the classical effective field theory, the word line effective field theory of the black hole to high orders in curvature? And I don't think it's clear. And
yeah, I mean, I think that's right. I mean, you could put it another way, that at 3 points we were able to connect amplitudes to black holes through this minimal coupling thing. It gave us there's these amplitudes, they're special, these minimal coupling amplitudes, and yeah, they turned out to be the Kerr thing. That was amazing, right? But we don't have that beyond 3 points. We don't really know what we're supposed to be comparing against. It's a bit of a big ask, right? We don't have anything like that for Schwarzschild, let alone Kerr, right? Something, a catalog of every effective operator for Schwarzschild. I'm not aware of one.
Well, there's a catalog. It depends what you mean by a catalog. How many R's?
Knowledge of the numbers. Knowledge of all of the numbers. That's what I want.
Which
That's
number?
Of course, I can write down operators, but
you mean all the love numbers?
Coefficients
yeah,
are.
Sure. Yeah, all the love numbers. Sure. I mean, there is debate whether they are 0 or not, isn't it?
All the dynamical ones. I mean, every operator. I don't think that's known. Maybe.
Well, I mean, at least for the R squares, I thought there was a debate whether for Schwarzschild they are 0 or not, isn't it?
Yeah, but I mean, R squared, that's a low power, right? I mean, I'm talking
about. Well, yeah,
but
if the R square is 0, then the higher ones surely are also 0.
Sure. Yeah, I agree.
No, there's no debate for Riemann square.
Definitely another story. Yeah.
For Schwarzschild, there's no debate.
Really?
About Riemann square.
Right.
Yeah. Yeah, I agree. But higher dimension operators, Ricardo, do you know? Like just for Schwarzschild, I mean,
you mean Riemann
people
cube
talk about them? Yeah.
Not that I know. Yeah, the point is, what do you relate them to? Because Riemann square, as you said, is the nice interpretation of the induced polarizability. But Riemann cube, phenomenologically, what would it correspond to?
Yeah, it's still an operator you could match to, right? I mean, unless there's some way of getting rid of these. I mean, of course you can get rid of some of them, but I'd be very surprised if you can get rid of all of them.
Yeah, then I guess it's very hard to, because you can make a 3-point computation, but then you have also to subtract the contribution to 3 points from the Riemann square.
Yeah, I mean, it's not going to be an easy thing, but I mean, there is an answer, right? I mean, like obviously the Schwarzschild black hole, that's the thing in general relativity.
But it sounds like what you want in the end, though, is a classification at the level of the amplitude itself, rather than the operators.
Yeah, that would be fantastic. Or well, yeah. I mean, I would like it that way, but yeah, Yeah. Just some knowledge. I mean, GOR spits out answers for these things, but they're not easy to get out of GOR. It would be nice to understand where these things are coming from in a more simple manner. Maybe in amplitudes. Certainly, amplitudes are great for minimal coupling for Kerr. It would be very nice to build on that to understand, the specific amplitudes and for these particular bodies that are intrinsic to general relativity.
I have a question for Radu. What do you mean by the fact that you have to have many spin together?
Maybe we lost Radu.
Yeah.
I think I understand what he meant.
Oh.
He's not there. I think he just meant a term in the answer with some power, non-zero powers of two spins, two classical spins of the black holes, of the objects, black holes to be. And if you have, well, the one loop calculation where this Compton amplitude enters, you can expand it in spins, and the problem that we anticipate, it should enter at the order spin to the fifth power, one of the spins to the fifth power. For example, spin of one particle to the fourth power and spin of the other particle to the third power, it could still be obtainable from the amplitude that is bad, but it's only bad at high orders in spin. And these high orders in spin are related to highest spin instances of that amplitude. But if you're at low amplitudes, at low spins, then you're probing, say, what Rafael was showing us was spin 1/2, and that was just only probing the dipole order in spin, and everything's fine with that. It's there's no spurious pole there in the spin 1/2 amplitude, and you can safely put it and hope that it reproduces something sensible, and it does. It's really at high orders in spin that we really don't know what to put there, and the only it's either the answer that looks bad, that has those spurious poles, or there's an infinity of answers that is no better than I don't know, having an infinite tower of some wordline operators put by hand and without any knowledge that it is a black hole, unless you have really some GR hard GR matching calculation that I think some people are trying to do now, but I have not heard about any new presentable results yet.
Yeah, actually, just one question about that. One piece of information that would also need to be put in is, the coefficient of the Lund number for short, or for Kerr. Right. I mean, that's another R² operator. It's in the 4-point amplitude for this object, right? And this Compton amplitude knows about the Love numbers. Is there some power accounting connection that relates the dimension of the Love number to this to the spin, like the 5/2? Or is it just? Yeah, I'm just wondering, is there? Well, it'd be cool if the failure of the of your Compton was at the same order as where you would need to put in the information about the Love number, because I mean, it would seem like magic to get that.
Is that are you asking me?
I'm asking anybody, but you were the last person speaking.
Yeah, I would say that that Compton amplitude knows about the zero Love number for the Schwarzschild black hole, because in the spin to zero, it just goes to the scalar particle limit, to the scalar particle amplitude. and that's the one being used already at much higher orders to producing good results. But well, that's the Schwarzschild case where the Love number is known to be 0. And assuming that it's also 0, the non-spinning Love number, then that amplitude is fine, right? It already has this information. If somehow the curl Love number was shown to be non-zero, then you would have to already modify that amplitude at the 0th order in spin. And as far as I understand, the answer is
I guess that
already
makes
matched
sense.
without that. So
yeah, okay, yeah, that's right. Thanks. Yeah.
So yeah, I guess that kind of means that we're sure that the curve Love number is 0 because we matched the scattering angles and everything to this order and with Kerr, and it's all good. I don't know. That's probably.
I'm not sure. I'm not sure. I think you're putting it in as nonsense.
Actually, there have been pieces of evidence that the Kerr-Love number in the static limit is 0, but then there was this paper I was referring earlier by Marc Casal and Alexandre Letiec that shows it's to be non-zero, but there is some discussion about the interpretation about the result. I'm afraid I'm not the best person to talk about the result.
Yeah.
Is anybody here familiar with the Alexander and Marc result? Let me see if I can point the finger to anyone here.
We will have some more discussion of this next week, I think.
Okay, so maybe we can.
There's a paper.
So basically, from what I remember from another discussion, is that what they found is that basically an effect that doesn't go to 0 in the static limit because they look at the result in some sort of co-rotating frame. That's why they see the effect to be static, which is kind of an artifact. But okay, I cannot say anything sensible. I mean, to summarize what facts are, facts are that there are indications that the Kerr-Love number is 0 in the static limit earlier than this Alexander and Marc paper, but then in their paper, they found a non-zero result. The discussion is about the interpretation of the result. If their non-zero result is really to be understood as a static contribution to the tidal Love number.
Yeah, so my question, so I would just wonder if that non-zero Kerr-Love number, how would it look like if you were to put this word line on the word, this Kerr black hole on the word line, right? So if when you put it on a word line, you don't create any new effective operators on top of the stuff that people have already been using to produce classical answers, with which the 2 p.m. calculation matched multiple 2 p.m. calculations matched in the quantum sense as well, then that amplitude is fine, right? You don't need to worry about that non-zero Love number. I'm just again saying that the amplitude, the Compton amplitude, when you take spin to 0, it is the massive scalar amplitude with which you can produce classical answers. And this when we match those classical answers, I understand that we match word line calculations. So
yeah, but you could always add to your amplitude, whatever the amplitude it is that the Compton splits out, right, with some coefficient. The Compton, or sorry, this Love number has some, it's an operator in your word line. There's an associated scattering amplitude that matches to it. You can just add that to your amplitude with some coefficient and then say that the coefficient is 0 in Schwarzschild. So you could always deform your amplitudes by just putting this in, right? it's a question what, you can match the coefficient from a GR calculation. Like say you shoot in a wave and you look at the wave scattering out to infinity on a Kerr black hole. That would constrain it, right? So you could match it, but this is just a question doing that matching calculation, not an easy calculation. But yeah, I mean, I think we'll hear more about it next week. I mean, I think it has been done at this point. Yeah. But I don't think scattering amplitudes are going to tell you what that is unless you have a principle saying, these are the right scattering amplitudes for Kerr as that object in general relativity. And I don't know of a principle that allows us to do that.
Yeah, absolutely. And as I was saying, I think the decisive information about this Compton amplitude will eventually come from the classical side, from matching to the classical information, rather than unless we indeed come up with some new principle to do these things.
Yeah, it's like something that distinguishes out a set of amplitudes that have certain properties.
Yeah.
Okay, so we have reached the time cutoff. Of course, people are free to keep discussing, but we reached the 5:30 in the European Central Time. So I am asking to the organizer, what shall we do next apart from going and starting the weekend?
I think that's exactly it. Have a look at the program of next week. It's still probably not complete, but it will be soon complete.